All right. Okay, so the documents I'll be referring to are those 3 that Lindsay has on the Padlet, and then the breakouts will actually be in the Jamboard. So don't worry about this second one here, because that's in the Jamboard. You do need those 3 documents that she pointed out. One says your turn, one has the cookie recipe on it, and one has some graphs. Great. Okay. Welcome back, everybody. Let me get my chat open. Awesome. Okay. Before we get started, I'm just going to drop in again. We have a Minnesota specific art of arithmetic to algebra that Lindsay mentioned. So I dropped that one in. Even if you can't attend, if you register, you'll get the recording. So there's that one that's coming up in October. And then we have a whole series between myself and my colleague, Danielle Sullivan, about mindset, growth mindset, increasing mathematical mindsets of students. And then every week we'll also have a progression such as this around math concepts. So it's alternating sessions of the pedagogy as well as the math concepts. So it'll run for 5 weeks. Again, if you register and you can't attend every session, you can access the recording. So just feel free to register. Yay. Okay, so here we go. So I have to shift my brain. We're going to all shift our brains. And now we're going to move into ratio reasoning, and we're going to connect it to linear algebra. So this all started for me when I was visiting several high school classrooms. And I was in a classroom and the teacher said, solve for X. So really kind of assuming this is a proportional relationship, because it might not be, but solve for X. And every single student did 1 times X equals 3 times 8 on their calculator. So they got 1x equals 24 and then divided by 1. Every kid. I was like, what? And I was like, wait a minute, like if this is a proportional relationship, like they grow proportionally, like you shouldn't have to cross multiply and divide by 1. Like you can think proportionally. Everything's been increased by a factor of 8. So 1 over 1 to 3 would be the same as 8 to 24. So it was boggling my mind. So that was the impetus for creating this session. Like, okay, we need to develop proportional thinkers, because really only 50% of the adult population can think proportionally, and we use it all the time. So cross multiply and divide really hasn't gotten us where we need to be. So this session will explore the development of proportional reasoning, which you have in your level D. We're going to use visual models. So these visual models, some you might be familiar with, some might be new, but we'll walk through all of them. And we're going to connect this to linear models, y equals mx plus b. And then really to allow vertical conversations to happen between your different levels. And then the most important outcome is that asterisk. Cross multiply and divide does not develop proportional reasoning at all. It's an answer getting trick, just like the kids were doing. They got an answer, but they couldn't tell you why that X would be 24. They had no idea about thinking proportionally. So that's why we need to help develop it through these visual models. Okay. All right. So we're going to start at the beginning with, what is a ratio? So you see some shirts on the screen. Go ahead and think to yourself, but don't hit send just yet. I want to give everybody some think time. Which statement represents a part to whole relationship and which statement represents a part to part relationship? So go ahead and think about that. You can type your answer in the chat, but don't hit send right now. Part to part, part to whole. Which one's part to part? Which one is part to whole? All right, go ahead and hit send. Good work. Good work. I like your shorthand there, Natalie. Love that. Good work. Great. Great. All right. Awesome. So hopefully you got those. So a lot coming through the chat. It was hard to keep up. Looks like everybody got part to part is 5 to 7. Part to whole, 10 solid t-shirts. I'm comparing it to my entire set of 24 t-shirts. So 10 to 24, 10 t-shirts out of my entire 24. So that's a part to whole relationship. And I'm comparing 2 parts, solid and patterned. I have 5 for every 5 solid t-shirts. I have 7 patterned t-shirts. So we can make some equivalent ratios. So then for every 10 solid t-shirts, I have 14 patterned t-shirts and make equivalent ratios. Great. All right. So we have 2 types of ratios, part to part and part to whole. Great. All right. Here is an issue. So solid to pattern, 5 to 7. I think everybody in the chat established this as a part to part ratio. 5, we have the colon to 7. I can use the word 2 for every 5 solid t-shirts. I have 7 patterned t-shirts. And then we often see textbooks say there's a third way. What's the problem with this representation? Good job. We just spent 2 hours talking about fractions. Yes, this is a fraction. It looks like a fraction. It's the representation has that fraction line. So we're assuming this is a fraction. We've already established this is a part to part relationship. Fractions are part to whole. So this is, there's a reason we use this, but we have to be really, really, really careful when we introduce this representation because we're not talking about a part to whole situation here. Okay. When we use this representation, we're actually using it as a rate, R-A-T-E. We're using it as a rate. So fraction notation is used, but this is not a part whole relationship. So then is it 5/7 or is it 7/5? It depends on what we're trying to find. Then if we're trying to find the number of solid t-shirts, the number of solid t-shirts will be 5/7 of the number of patterned t-shirts. If we're trying to find the number of patterned t-shirts, it'll be 7/5 of the number of solid t-shirts. If that is messing with your brain, let me add an equation. Is 10 5/7 of 14? There were 10 solid t-shirts and 14 patterned t-shirts. Is 10 5/7 of 14? Yes. So if I want to find the number of patterned t-shirts, 14 would be 7/5 of 10. What? So we use that third representation, but it's not a fraction, it's a rate. Okay. All right. Let's see the chat. Fraction denominators are parts needed for the whole. All fractions are ratio. All fractions are ratios. Not all ratios are fractions. That is messing with my brain. 7 to 5. All fractions are ratios.
A ratio is simply a comparison of two numbers. A fraction is a comparison of a part to a whole. So fraction is a specific ratio where one of the values is a whole. That's what I teach my students. So.
Okay, I'm gonna have to think about that. All right, so part to part, part to whole, and rate. Andy. Your name, I had a friend and a colleague whose name was Albie. So I accidentally used your last name as your first name. Okay, so we're gonna hop in to level C visuals, but they're mostly level D visuals. So a kind of a range across your C, but mostly in level D. Those documents I had you print, you're going to do the work on there, or you just use pencil and paper. I'll have them on the screen as well. But I will have you, I'll introduce the model with an example on the screen, and then I'm going to have you do it on that practice page. So the your turn practice page is where you are practicing the model. All right, so here we go. We're going to start with a tape diagram. So this is also referred to as a bar model. Our situation is a cookie recipe uses 2 cups of sugar and 3 cups of flour. Create a tape diagram to represent this ratio. So if you've never done this before, you're just going to draw parts. So I have 2 equal parts to represent my sugar, and I have 3 equal parts to represent my flour. So I have 5 parts total. 2 cups are sugar and 3 cups are flour. All right. All right. So go ahead and do these 2 problems after you've written your bar model. Find those 2 answers. I'll give everybody think time, so don't type them in the chat just yet. So draw and then answer those 2 questions. I'm going to read the chat while you do that. Okay. All right, go ahead and write your answers. What's a 1 part to whole ratio? And if there are 27 cups, how many cups of sugar would there be? So go ahead and tell us 1 part to whole ratio. All right, nice work. We're getting our cups of sugar. And if someone could also type in there are 2 possible part to whole ratios. So what would one of them be? Nice. Thank you, Mark. Thank you, Natalie. Awesome. Okay, so this is a part to part ratio. For every 2 parts of sugar, I have 3 parts of flour. If we want to look at part to whole, for every 2 parts of sugar, for every 2 parts of sugar, for every 5 cups of the total cups of dry ingredients, I guess. All right, now the next one, if there are 27 cups of flour, how many cups of sugar would there be? So if I have 27 cups of flour, I can fair share my 27 cups, and each of those boxes would get 9 cups. So it's all been scaled up by a factor of 9. So that means I need to scale up my 2 parts of sugar. Each part gets scaled up by a factor of 9. So that would be 18. So 18 cups of sugar, because everything, just like we talked about with fractions, everything kind of gets scaled up by the same factor. Great. I'm seeing these explanations in the chat. Fantastic. All right. So your turn. Create a tape diagrams to represent the following quantities. Chris mixes 4 cups of cereal, 3 cups of pecans, and 2 cups of raisins to make a snack mix. So create a tape diagram to show that. And then just put okay in the chat so I know that drawing has been completed. Give everybody a chance to draw. Let me know if you have your tape diagrams ready. Ooh, Justine with the thumbs up. All right, looks like we're good to go. All right, so mine might look like yours. You might have raisins on the bottom. I kind of did mine out of order. Doesn't really matter. Make sure all the parts are the same size. So visually, they all look the same. 4 parts of cereal for every 2 parts of raisins, for every 3 parts of pecans. A little difficult to do cross multiply and divide when you've got 3 things you're comparing. So let's answer some questions. So here you go with your tape diagrams. First off, how many total cups of ingredients are in one batch of mix? And then if you make a large party, if you have a large party and you make 45 cups of the mix, keeping the ratio the same, how many cups of each ingredient will you need? Go ahead and do that. You can type your answers in when you're ready. So this is a multiple part one. So go ahead and type your answers in whenever you're ready, whenever you solve it. All right, we're seeing answers come in. Nice work. All right, nice work. Great. All right, so there were 9 cups in one batch. Ding, 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 ding. And here are the ingredients, 20, 10, and 15, which I believe most everybody said. You got it. All right. So interesting. You had to start with 45. So isn't that interesting? 45 cups of snack mix. So that means if there were 9 cups in one batch, I have 45 cups. Everything was increased by a factor of 5. So the cereal, all those boxes were increased by a factor of 5. The raisins were increased by a factor of 5, and the pecans were increased by a factor of 5. So everything has been scaled up. So to create equivalent fractions, equivalent ratios, to maintain equivalent ratios, all of the parts have to be scaled up by the same factor. Scaled, because they could be scaled down, like, by 1/2 or something, but they all have to be scaled by the same factor. Okay, all right. Tape diagrams. I see this coming up in the chat. Tape diagrams are fantastic. It's a physical model. It's a concrete representation of the ratio. And it is really, really easy for students to create equivalent fractions just using simple sticky notes on their desk. So they could draw these. Sometimes it's hard for kids to draw these and be precise with the size. So just take sticky notes, and have them put it on their desk. So I need 2 sticky notes to represent my sugar, and I need 3 sticky notes to represent my flour. And now, oh my gosh, I have 27 cups of flour. So you hand the 27 cubes or 27 counters or 27 whatever, 27 paper clips, and have them fair share it into the boxes. So they're fair. So kids that aren't good with division, they can still create equivalent ratios. So take the 27, fair share them. Each sticky note is getting how many objects? I don't have any 27 left anymore. They've been distributed to my 3 sticky notes. How many are in each sticky note? There's 9. Oh my gosh. Well, now then I need 9 in each of my sugar sticky notes. And so nice, easy way for them to arrive at that answer of 18 like you all did. So tape diagrams are just awesome. Great for kids that struggle with division. Okay. Okay. All right, cool. So everybody good with tape diagrams? They're one of my favorites. All right, let's go on to something that's probably a little more familiar, which is a ratio table. So here we're going to use the same problem, 2 cups of sugar for every 3 cups of flour. What I'd like for you to do right now is keep the ratio the same and find the missing quantities. So go ahead and take a look and just kind of think what the numbers would be to fill in the missing quantities. And actually, we're going to use this later. So go ahead and make a table on your paper and record the quantities. You're going to use this later on. Okay, no need to type any answers in the chat on this one, just record it on your paper. So you make a ratio table on your paper with all of the quantities filled in. While you're doing that, I just want to say I'm amazed at the ASL interpreters, and you switch off. How much time? I think you're on for a few minutes, and then you take turns and the next one comes on. Is there a time that you switch? Somebody can just type in the chat for me. Awesome. All right, here are the answers. So make sure your ratio table matches the answers up here. So I have 2 cups of sugar for 3 cups of flour. So on the next line, I have 4 cups of sugar and 6 cups of flour. I have 6 cups of sugar and 9 cups of flour. 8, 12, 10, and 15. Okay, awesome. All right, now, if I had a ratio table where students only added, I would not develop proportional thinking. So a nice key feature here is you want to come up with problems that force students to use multiplication or division. So they have to fill in these missing boxes, and they can't always do it by adding, because if they're only ever adding, then they're not thinking multiplicatively in that proportional way. All right. So now let's identify some relationships. If I put my tape diagram up in the upper corner so you can see the concrete model. So I have 2 cups of sugar. If I want to make another batch of cookies, I'm going to need another 2 cups of sugar. And then since I added 2 cups of sugar, if I'm making another batch, I need to keep my ratio the same, and I need to add another 3 cups of flour. So when they add, they're adding 2, they're adding 3, they're making an equivalent ratio. But I want them to think about multiplication. So I'm going to say, just like we talked about, 2 groups of 2 cups. This is 2 groups of 2 cups. And we know from that language of multiplication, that's the same as 2 times 2. And 2 groups of 3 cups is the same as 2 times 3. So both quantities were increased by the same factor. Sometimes we switch every 15 to 20 minutes. Oh, cool. Awesome. All right. So if I have 6 and if I want to make a third batch, I'm going to add another group of 2 cups. So I would have 3 groups of 2 cups. I would add another 3 cups of flour. So I would have 3 groups of 3 cups of flour. So 3 groups of 2 cups and 3 groups of 3 cups. So both quantities were increased by the same factor of 3. Now we're thinking proportionally. We've increased everything by that same factor. All right. Awesome. All right. So that's how we get to equivalent fractions with our batches. But now I'd like for you to look at the relationship within the 2 ingredients. Is there a relationship between the 2 cups of sugar and the 3 cups of flour? What's the relationship with the 2 and the 3? What's the relationship with the 4 and the 6? What's the relationship with the 6 and the 9? Another way to think about it is how much sugar is the 3 cups of flour? The 3 cups of flour is how much of the sugar? Is how the 3 is how much of the 2? The 6 is how much of the 4? Does that mess with your brain? All right, going across, 3 is always 1.5 times the 2. 6 is always 1.5 times the 4. 9 is 1.5 of the 6. I could go the other way. 2 is 2/3 of 3. 4 is 2/3 of 6. 8 is 2/3 of 12. Okay, so there's a relationship that goes back and forth. Thinking about our t-shirts, we had 5/7 and we had 7/5, depending on what we were trying to find. So this works the same way. Either have 3/2 or I have 2/3, depending on what I'm trying to find. Okay, awesome. All right, so type in, or anybody having any ahas about that? I'm sure everybody's familiar with a ratio table, but any ahas about the depth that is happening in a ratio table? Great. Okay, so here's your turn. I've actually oriented the ratio table in a different way. So what I'd like for you to do right now is develop a ratio table. I put that note up there, resist the temptation to cross multiply and divide. So you go to the store, you buy 3 comic books, and your total cost is $7.50. So use your ratio table to figure out how much 5 comic books would cost or how much 8 would cost. I'll get you started here. $7.50 for 3 comic books. So go ahead and work on that and just type an okay in the chat when you're ready. Okay, and I'm not sure what I'm just getting to the chat right now. So Lindsay, something about Laura's explanation, but I don't know what that was.
Yes, I think it was potentially looking at a pattern between each number, that the difference from the first 2 between 2 and 3 was 1, the difference between 4 and 6 was 2, the difference between 6 and 9 was 3. And so like looking at a pattern that's not necessarily multiplicative.
Got it. So what, how can we help students not do that? I guess is the question. So how can you present this so they're not looking at it as the difference? I wonder if connecting it with a ratio with a tape diagram helps. So they're recording the values in the chart as they're scaling up on the concrete model. Okay, let's think about that. Let's come back to that after we do this one. Okay, so yeah, let's talk about that after we do this one. So $7.50 is the cost for 3 comic books. So Lisa's put in 1 comic book is $2.50. All right, so we find that unit rate. Fantastic. So we have to go backwards to go forwards sometimes. So in this case, if I know that it's $7.50 for 3 comic books, how much would 1 be? So I need to divide both numbers by 3. Or I could I could take my 3, take $7.50 with coins, fair share all of it into my 3 sticky notes. And then one of those sticky notes will have $2.50 in it. So the unit rate is $2.50. And then once I know that unit rate, I can use that to find the cost of any number of comic books. So in order to find the cost of 5 comic books, I'm going to take 1 comic book times 5, because I now have 5 comic books. So I have 5 groups of a comic book. So I need 5 groups of $2.50. Again, kids could chart this out not only in their ratio table, but do it on sticky notes. If we know that 1 has $2.50, what would 5 comic books look like? Put their 4 more sticky notes out. All right, we need $2.50 in each of those sticky notes. Okay. Same with 8. So if I have 8 comic books, I need to multiply by 8, and I multiply my $2.50 by 8 to get $20. Okay. All right. So here's the interesting part. We multiply both by the same factor to make those equivalent ratios. So 1 times 8 is 8, $2.50 times 8 is 20. So one way to get equivalent ratios is to multiply all the parts by the same factor. We talked about that, and we saw that in the sticky note. The other way students need to understand ratios are equivalent is that they have the same unit rate. So right here, within $7.50 to 3, I can boil that down to $2.50 for 1. The same unit rate is in that ratio. If I look at $12.50 and 5, I can divide both of those by 5 and I get $2.50 for 1. Same with the 20 and the 8. I can divide by 8 and I get $2.50 for 1. I mean, it's not, we're talking about really 2 sides of the same coin. I multiply by 8s and then I get my equivalent ratios, but then I can take my ratio and I can divide by 8s and get to the unit rate. So students need to see that they can multiply and create equivalent ratios, but they also need to see, in order to be an equivalent ratio, you have to have the same unit rate. So equivalent ratios, and that's the key of proportionality. Equivalent ratios are created by multiplying the values by the same factor. So we talked about that, but equivalent ratios have the same unit rate, and this unit rate is identified as the constant of proportionality. Okay, so to be an equivalent ratio, to be proportional, you have to have the same unit rate. Okay. Let me know if there are any questions on that. And then let's go back to this. So let's go back to this one. So right here, when we're talking about this is the unit rate. So for every 1 cup of sugar, there's 1.5 cups of flour. So I'm not sure how to move students away from the quantities per se, but we need to move them into this constant proportionality, what's always happening between those 2 values. And it's a constant of proportionality. It's the unit rate. So I wonder if taking them 1 step further and drawing up above, 1 cup of sugar is 1.5 cups of flour. So maybe positioning that and now check it. So do all of these pairs have the same unit rate? That might help them move from that question or that concern that came up earlier. Okay. All right. Okay, let me know. It's hard for me to do the chat. So let me know if there's something that comes up in there that we need to stop and talk about. Okay, so we've done ratio tables, we did tape diagrams. Now let's look at double number lines. My husband is a high school chemistry teacher, and he uses double number lines all the time with his students. It's his number one go-to for proportional thinking when they're doing chemistry problems. It's all about proportional thinking. So here we go. All right, so double number line is a number line that we just spent this morning doing, but we're going to have two parts on there. So every time we partition someplace, we're making an equivalent ratio. It's really, really cool. So here's our comic books. We're same comic book problem, but this time draw a double number, or a number line. And what I'd like you to do with each of those tick marks, the tick marks are going to mark two things. You're going to have marking comic books on the bottom, and you're going to mark the cost on the top. So every tick mark is going to make an equivalent ratio between the cost and the number of comic books. So I started you off with 3 comic books. Right above that, I put $7.50. So there's $7.50 for 3 comic books. Oh my gosh, and somebody just put, Pamela, this is like my favorite book ever. Thank you, Amber. Favorite book ever. It's amazing. Okay. So let's see. I have 3 comic books cost $7.50. How much would 1 comic book cost? So between 0 and 3, I'm going to partition that into 3 equal spaces. So I'm dividing by 3. So I'm making a cut, and I'm making 1. So inadvertently, I also have to partition my $7.50 into 3 equal parts. What? So I end up with $2.50. There's my unit rate on the double number line, and then I can use that to find the cost for any number of comic books. What if I have 2 comic books? So 2 groups of size 1 is 2. 2 groups of $2.50 is 5. So I'm using that number line. I'm making jumps. I'm making jumps for comic books, and I'm making jumps for the $2.50. Okay. All right. Any ahas going on about the double number line? It is one of my favorites. So if I want to find the cost of 5 comic books, I multiply $2.50 times 5, and I multiply the number of comic books times 5. Okay. How is using a double number line similar to a ratio table? So think about that and type your answer in the chat. How is a double number line similar to a ratio table? While you're doing that, she also has lessons. I don't know if you knew this one. Same author. I love it. Horizontal instead of vertical. Oh yeah, Lisa, it's kind of like a ratio table on its side. Love it. So rather than moving down and multiplying, they're moving across, they're moving to the right or to the left. Great. Equivalent, different visual, shows the same information. Yeah. Helps lay the foundation for graphing. A double number line is a horizontal ratio table. I love it. Good job. Great. All right, your turn. So go ahead and draw one. We're going to assume he runs at a constant speed. That's a big assumption. So Zachary exercises at a constant speed. During 1 week, he jogged 36 miles in 6 hours. Show the relationship of miles and hours with a double number line. So your turn to draw one. And then just give me an okay. And you have that drawn. Fantastic. All right. Hopefully yours looks like mine. Okay, so here are a couple questions for you to answer. How long will it take him to jog 24 miles? How far will he travel in 4.5 hours? Go ahead and figure that. Okay, go ahead and type your answers in the chat. Great. All right. So the first one is 4 hours. You can see that one right there on the chart. So we can use that to get our answer. 24 miles, you would do that in 4 hours. And then how far will he travel in 4.5 hours? That one is not on it. So we had to do a little bit of thinking because as somebody said in the chat, he's not running the whole hour. He's only running part of the hour, half of the hour. So that makes us think about, all right, what is happening between 0 and 1? I noticed some people caught and revised their thinking and added the 0 onto their number line because there is something happening within that hour. What if I only want to run a third of an hour? What if I only want to run half of an hour? I still am traveling some distance. And in this case, a half of the hour is also half of the miles, assuming he's running at a constant speed. So in a half an hour, he would run 3 miles. So another equivalent ratio. Isn't that cool? And so between 4.5 and 4 and 5, he would run 27 hours. Lots of ways to get that. We can think about 24 and I need to add 3 more miles because he's not running the whole 6. He's only running halfway. Maybe you thought about the 0 and 1 is going to be 3. And then so you counted 3 more on from 24. However you thought about it, the answer for the second one is 27 miles. Good job. Yes, and bringing it back to equal groups and fractional parts. Absolutely. So there is something going on between the 0 and the 1 in this particular case. Great. Good work. Great. Oh, we already talked about that. Using double number lines with percents. Okay. Any other thoughts on the double number line and ratio tables? Okay, but wait, there's more. Using double number lines with percents. All right, so draw a double number line. Let's put 0 and 1. And now I want to compare that with percent. All right, so first question, is this a part-to-part relationship or a part-to-whole relationship? Percent. Is percent part-to-part or part-to-whole? Part to whole. Ding, ding, ding. All right. So let's go ahead and partition our double number line into 4 equal parts. 4 equal parts. So each part is a fourth. So it's a fourth of my whole, and it's a fourth of the 100. So 1/4 is worth 25%. I think everybody agrees on that. So 2/4 would be 50%, 3/4 would be 75%. Okay. All right. So this right here is just something kids always struggle with the relationship of percents and decimals and fractions. So doing a double number line and then adding decimals onto it, this right here is a great activity. The numbers are the same, they're just different representations. They occupy the same spot on the number line, they're just written in different forms. So, you know, just have them do this. Okay, what do tenths look like? What percent of 10 is 1/10? And have them, you know, just have them draw it out so they can visually see they're all the same. They're just different representations. Okay. All right. So each section is worth 25%. And it is a part to whole relationship. Okay. So now I want to ignore that whole type the answers in the chat thing. I want to think about this. If I go to the store and something is $40 and it says it's marked down 25%, I'm going to tell you honestly, I do not set up a proportion, cross multiply and divide and subtract from my total cost. I just don't do it. I take that cost, $40. If it's 25% off, I'm going to partition that into 4 equal parts. Each one is worth 10, and I'm going to subtract it. That's what I do. I'm sure a lot of you on this call do the same thing. I don't set up a proportion, cross multiply and divide, do all that thing. I don't do it. So I, you know, just like mentally use my mental math skills, and the double number line is a terrific visual of exactly what we're doing in our brain. So here I have the $40. If it's 25% off, well, I know that half of it would be 2 pieces of size 1/4 would be $20 if I wanted to think about it that way. So that like one of those pieces will be $10, and I'll just take that off the price. So I'm going to pay $30. So just a really great visual to help kids with percents. That's not complicated at all. All right. Okay, so your turn. Draw a double number line. At tryouts for the school talent show, 60% of 30 performers played a musical instrument. How many performers played a musical instrument? So this is a 30 performers is your whole. So draw a double number line, see if you can figure that out. Give me an okay in the box when you have drawn it, or you can type your answer in the box, that's fine too. Oh, I think I had the 25 up there on the left-hand side, but I would subtract. Yeah, don't know. My visual was not what was in my brain. Sorry about that. I think I meant to move the 25%. I'm answering Amber's question. All right, so here we are. 30 performers. If all 30 played a musical instrument, that would be 100%, but only 60 played a musical instrument. In mine, I like to think in 10% increments. I don't know, that's just what my brain does. So I did 10% increments. So I partitioned it into 10 equal parts. And so each part was worth 10%. So then so if I divide my 100 into 10 equal parts, then 30 gets divided into 10 equal parts. So each 10% is worth 3 performers. So I'm going to need 6 groups of 10%. So I need 6 groups of 3 performers, which is 18. Okay, and I saw 18. I saw Mark put in there 10% is 3. Some of you may have done it in half. Like maybe you started in half and said halfway, 50% is 15. And then you need to figure out what the group is to get to 60%. But I kind of went down to a 10% and then multiplied by 6. Lots of different ways to solve it. That's just how my brain works with the 10%. Okay. Great. Some of you may have thought with 15. All right, let's see. Students collected. Do we have a breakout? We have a breakout coming up, right? Okay, let's just skip that because I'm looking at the time here. And let's do, let's go into our breakouts. And we'll keep the same time that we established. So breakouts, and we're back in action. It always moves everything though, and I come back. I have to put it all back in the spot I want it. Great. Okay. So thoughts about double number lines. My group is having an interesting conversation. Anybody want to come off mute and share their thinking around double number lines?
I'll go. I really like the relationships that we're making here because it's difficult for students if things aren't 100 as the number for 100%. They have a hard time visualizing that 900 means 100% of the people that we're surveying. So I like how that combines those two different, they feel very different to a student, but yet this just shows them that it is the same, that you can take a different number than 100 and it means all of them, 100%.
I love that. All right, so thinking about that, Emily has, I love the way it shows relationships. Never used, but now I will. Means the whole. Yeah. Okay, I don't know who came off mute to talk. I didn't catch your name, but that made me think about this problem. We skipped it, but I think I actually want you to do it. So go ahead and do this problem on your paper. Students collected 600 cans for the canned food drive. That was 80% of their goal. How many more cans do they need to collect to reach their goal? So this is slightly different. Students really have to think about the situation here. So try this one on a double number line. And then just give me an okay in the chat when you have an answer. This one must be a stumper. All right, I see some thumbs up in the boxes and in the chat. Okay, all right, so let's see how you did here. So there's my line. Students collected 600 cans for the canned food drive. That was 80% of their goal. So do we know what the 100% is? We do not. All we know is that they have some cans and that's 80%. So we don't know what the quantity is for the 100%. So again, this is a great visual model for students. 100% is going to be all of it, but I don't know what all of it is yet. So this just is a great, really great tool for problem solving. But I do know that 80% is 600. So 8 groups of 10% or 81%. Like you can divide down and get to whatever you want to use that to go forward. 10% is going to work out okay for me on this one. So I'm going to divide by 8. So I divide the 600 by 8. Again, there's that proportional thinking. And I get 75. Great, 75. Is that my answer? No, it's not my answer. What is the answer? Type it in the chat. How many more cans do they need to reach their goal? I love it. I saw somebody type in 750, which is awesome. So 750 was their goal. Fabulous, whoever put that one in. And I see Kevin put it in as well. That's the goal. And so how many more cans do they need? 150. They already have 600, but great thinking, because 75, the total was 75. So it's exactly what we need to solve this problem. We need to know that the goal was 750. So they're going to need 150 more. Absolutely. And like, that's just another great thing of like, oh, great, you found the 750, but let's read one more time. What is it we're trying to find out? We need to know what that difference is between the 600 and the 750. Great. Oh, I love that. I found half of 600, which would give you 40%, half of 80. And then we need another 20%. So we need half of the 300, 150. Love that. I think that was Natalie. I saw it went up in the chat there. Beautiful, beautiful. Nice thinking, everybody. Good job. So again, you can use a double number line when you don't know what the whole is. So, or the 100%. Great. Okay. All right. You're going to shift gears and grab the document that says putting it all together, which is for the cookie recipe. So, I don't know if I have a copy here. I'm going to hold it up, but it's one that looks like it's got some grid paper on it. So it looks like this. You already did the ratio table, so I'll put the answers up here on the ratio table. The first thing I would like for you to do is to plot those points on your grid paper. So you should have a little piece of grid paper on that document, and you're going to plot the points from our ratio table. I've already decided that I want sugar as on my x-axis, so I put sugar on the x-axis. So for every 2 cups of sugar, you need 3 cups of flour. So go ahead and plot that point. So these are your ordered pairs, 2, 3. So when we, whoops. Oh, I thought I had lines. Anyway, 2, 3, that's going to be your first ordered pair. Let me see if I can find that. Yep, here it is. Okay. So 2, 3, you're going to plot that there. 4, 6. All right. Okay, and then there are some questions for you to answer underneath. After you plot those points, is it a linear relationship? How is the slope related to the ratio? Can you create an equation? And what is the constant of proportionality? So go ahead and complete that. Give you some time to do that. Okay, all right, so let's see how we're doing here. Okay, anybody come up with an equation? Anybody come up with an equation to represent the amount of flour needed for any amount of sugar? Okay, I see some answers coming in the chat. All right. Okay, so a couple ways we can write that. We can say the amount of flour that's needed is equivalent to 3/2 or 3/2 times the amount of sugar. Or we could say the amount of flour is 1.5 times the amount of sugar. So interesting, for every 3 cups of flour, we have 2 cups of sugar. We can distill that down to a unit rate, which would be 1.5 cups of flour for every 1 cup of sugar. So there's an implicit 1 here with this unit rate. Okay, now a lot of times we hear slope needs to be as a fraction. Well, not true. Slope can be represented as a decimal because there's an implicit 1. It's a rate. Slope is a rate. It's not a fraction. We've already established that. It looks like a fraction, but it's not a fraction. It is a rate, and it is the constant of proportionality, and it is the unit rate. So here is your line. We plotted those points. For every 2 cups of sugar, we rise 3 cups of flour. So for every input of 2 cups, our difference is 3 cups. There's a nice high school standard, equal differences over equal intervals. For every interval of 2 cups, our difference is 3 cups. But let's see what's happening at the unit rate level, what's happening for 1 cup of sugar. So for 1 cup of sugar, down there at the bottom of my graph, for every input of 1 cup, my rise or my difference is 1.5 cups of flour. So for every 1 cup of sugar, my difference is 1.5 cups of flour. So we saw that unit rate in the ratio table. We saw that unit rate happening when we made equivalent ratios. For every 6 cups of flour, there are 4 cups of sugar. 6 is 1.5 times 4. So that constant proportionality shows up in a lot of places, and in the graph, it's the slope of the line of a proportional relationship. What? So when I say cross multiply and divide doesn't develop any of this, it doesn't develop any of this. So there's a direct correlation between ratio thinking and linear models. And you can see that right there, where the slope of the line of a proportional relationship is the unit rate. Okay, all right. Type any ahas you're having in the chat while we go through this. The tape diagram maintains that concrete visual. We started there. The ratio table and the double line helps us record equivalent ratios. So we did a lot of practicing of recording equivalent ratios. And then in a graphical sense, the slope of the line of the graph represents the rate that's always the same in equivalent ratios, that constant of proportionality. So in a proportional relationship, the slope of the line is that unit rate. What? Mind blown, right? I hear brains exploding all over Minnesota. All right, if we focus on rise over run, and students are just counting squares, it's going to lead to some misconceptions. So on this particular one, on the left is how it should be drawn. On the right is scaling it, weirdly, because kids kind of scale things all over the place. And if they're just counting squares, they're going to say the slope is 1/1. For every 2 cups, I go up 3 cups. I went over 1 spot, I went up 1 spot, and it's 1/1. So they have to think in intervals. For what's happening for every 2 cups, What's happening with the flowers? So we need to transition them, not to just count spaces, but to actually think about what's happening with those intervals and the differences. Okay. All right, we're going to skip this. Boom, boom, boom. And I can't remember. Oh, okay. I think I'm going to skip this too, because we have to, you can do this one in the afternoon. So that was just taking, you're going to do the same process with a different problem. So you can use that page 5 in the afternoon session, because I think what I want to do is do this. I'm looking at my time and I saw Lindsay's chat. So let's go to this one. So you'll need the third document, which was comparing 2 different stalls, stall A and stall B at a farmer's market. So I'm going to show them on the screen. For each situation, I want you to look at the table and the graph and think about, is it a linear relationship? Is it proportional? And how do you know? Okay, so here's the first one. We're buying grapes, so pounds of grapes and the cost. So take a look. Is it a linear relationship? Is it proportional? And how do you know? So I'll give you 15 seconds to think about it. And then type your answer in the chat after 15 seconds. All right, go ahead, let her rip. Linear, proportional, how do you know? All right, I see answers coming in. Yes, it's linear. It's linear because if I connect those, I can draw a line visually. It looks like for every 2, it's going up the same amount, same rate of change. Love that. Is it proportional? Yes, it is proportional. How do you know? How do you know it's proportional? All right. It is proportional. 2 ways we can think about this. Number one, I can draw the line and that line will go through the origin at 0, 0. So we can intersect the y-axis at 0. Great. But I want to force you to the ratio table. What's happening in the ratio table? So use the ratio table to support your reasoning that it's proportional. When I look at the ratio table, I need a relationship between the cost and the pounds that has to be constant. So 4 is always 2 times 2, 8 is 4 times 2, 12 is 6 times 2, 16 is 8 times 2. So my constant of proportionality is 2. Great. All right, stall B, take a look at this one. Same questions. Is it linear? Is it proportional? How do you know? All right, go ahead and type in the chat. Linear, proportional, how do you know? Tricky, tricky. It is linear. Yep, it is linear. Is it proportional? Not proportional. How do you know? Woo, Tom, busting it out. If I draw that line, it's not going to go through the origin, but that's like so easy, right? That's like, oh, but we want to push thinking. So go back to the ratio table. Is there a constant of proportionality? 2 times 4 is 8. 4 times 4 is not 10. 6 times 4 is not 12. All right, so I don't know. There's no constant of proportionality. 8 divided by 2 is 4. 10 divided by 4 is 2.5. So I don't have a constant of proportionality. So this is the difference between y equals mx, which was proportional, and y equals mx plus b. So this one, I have the $2 per pound for the grapes, but I have an additional cost of maybe a one-time cost of renting the stall that was $6. So it pushed my line up. So I have a constant rate of change. I have a constant rate of change, $2 for every pound of grapes, but I do not have a constant of proportionality because it's not a proportional relationship. We often see this. Kids will set up proportions and cross multiply and divide, and it's not a proportional relationship. A classic problem is the cricket one. You guys probably all know this. The cricket chirps so many chirps at a certain temperature, figure out what the temperature is. And kids will always number pluckers. They pluck the numbers, they set up a proportion, they cross multiply and divide, and they get the wrong answer because it's not a proportional relationship. So we have to help them with that. Okay, so here are the two graphs simultaneously. The top one is proportional. It'll go through the origin, and there's a constant proportionality. The bottom one, it's linear, constant rate of change, but it's not a proportional relationship. So that rate of change is not the constant of proportionality. Okay. So all proportional relationships are linear, but not all linear relationships are proportional. I'll leave you with that. Haha. Okay. All right, I think Lindsay had some comments, some things to make. It is 12:16. I did pretty darn good. So that is my email address. If you have any questions about any of this, do let me know. I love to talk about math, as you can tell. Thank you for your participation. This was fantastic. You all are great audience. Thank you so much. And I'll drop it in one more time. Feel free to come and join me with any of my other sessions that I have going on.
Thank you for saying that, actually, because I wanted to ask, how would we sign up for the Mathemagical webinars?
Yeah, so this one, it should be, hopefully it's working. I just dropped it in there. If you download it, it should be linked. Is it not linked?
I don't think it's linked. Maybe I missed it, but I opened it and I saw all the dates and titles, but I didn't see where to register.
Let me try it here. If you, is there a registration? Okay, well, let me stop sharing and let me go and find out. Let's see, if you click on that.
I will pull up.
Oh, okay. Huh, on the one they sent me, it was like, it was live to link it, but okay, let me try something. Go ahead and talk and I will figure it out and be right back.
Sounds good. No worries. Thank you so much. I mean, that was amazing. And if you have any questions, if anyone has questions that Liz could maybe quick answer, put them in the chat. Otherwise, I am going to go over a few logistics. On the Padlet, if you refresh the page, if you're on it, you will notice that there are a few more resources. So I put a blank copy now of both of the breakout room Jamboards so that you can see the problems and try them on your own. I also over here on the links shared in the chat, we have the event flyer, which I'll come back to in just a moment. And then I know that there were some links shared as we were going. So those are just in their own column, events to register for, and then also these flyers that Liz put in the chat. And so I will get the live link one for the Mathemagical Mindset webinar series uploaded once we get that. But otherwise, what we're gonna do, we're gonna get ready for lunch. And once we come back, we will not come back to this room. So you will use your flyer to find what session you would like to choose and attend after the lunch break, and it will start at 1:15. And yes, thank you, Marisa, for putting it in the the chat here. So there are 4 concurrent sessions. One session, 2 of them are actually about formative assessment and looking at student work of some of the problems that we talked about today, and being able to analyze, okay, what do students know? What might be some misconceptions? What would we do next in our instruction, and kind of diving into that. So one focusing on moving beyond cross, multiply, and divide, and the other on fraction computation on number lines. And then the other 2 are reflection sessions. So if you're like, I don't really want to analyze student work right now, I just want more practice with these problems myself, because yes, we all know how to do these, but the articulating the reasons why behind it and using number lines and some new strategies, these sessions would then be for you to just get some more time to ask questions about what we talked about this morning. So at 1:15, you will choose a session, and then we'll repeat all 4 of them. And then at 2:15, you will choose another session. And then that'll be the end of the day. And like Patsy said in the morning, the evaluation and CEUs, you will find here. This is how you will get that, by filling out the evaluation. Yes, what am I missing? Anything? Any questions?
Lindsay, there's a question about having access to the videos of the other sessions if we don't attend those.
Oh, yes. I'm going to let Marisa maybe answer. Will they only be on the YouTube? Would we be able to put them on the Padlet? Is that a no? I don't even know. Can I upload a video?
I can answer that, Marisa, if you'd
Please,
like.
yes.
We will definitely upload those to the YouTube channel, and they'll be in a playlist for the Math Institute. And then we could very easily drop them in the Padlet as well, just a link to those, if that's easier for everyone to have stuff all in one place. That's easy enough. And then, as Gail writes in the chat, thank you, Gail, you'll also get an email next week with the flyer, links to those recordings and the evaluation links. So if you don't get to it, if you need to rush out, write us things, finish up today, we understand, and we'll nudge you next week gently and kindly. So, and I want to add my thanks to, I hope you've been watching the chat, Liz. Everyone's just singing your praises. So thank you so much for all of your time this morning and your expertise. This was a wonderful session.
Oh, great. Thank you so much. Thank you. You all are awesome. This was just so great. Such a participatory audience. I love it. I dropped the link in. Hopefully that works. It says Cvent, and it looks like she's going to it. You got it. And you just register there. And so if you can't attend, you'll be able to access all the recordings. And then the other one, I believe, was just for Minnesota. And that one should be a live link as well. Scroll up. Let's see, I'll drop it again in the chat here, the Minnesota one. And that was for the arc arithmetic to algebra, which some of you may have already seen.
And I think that one was linked on the PDF. I saw that one. Yes, perfect. Yeah. So that one is on that one will work on the Padlet, and then I'll just exchange. I'll add the link here. So we can register.
Fabulous. Yay.
Thank you so much.